Hello everyone, welcome back to Random Matrix Theory. In this video, we'll start our discussion on random matrix theory, and in the previous videos, we tried to cover the prerequisites of the course, and I believe almost all the tools necessary for RMT is somewhat sorted. So we can start the course. But first, what is RMT? So RMT is a marriage between linear algebra and probability. And by the end of the course, we'll try to see if it's a happy marriage or not. But for me, it's already a very happy marriage. Okay, so first, what are random matrices? What are random matrices? What are those? So random matrices, as the name suggests, they're entries or let's say Aij, the entry, a random element Aij of the matrix is taken. So element, let's write like this. Element Aij of a matrix, they're taken randomly from a distribution or an ensemble, so they're random variables. The elements of the matrix are random variables. So elements Aij, they're drawn from, let's say, an ensemble or a distribution. Well, not necessarily a single distribution. It can have, the elements can be drawn from multiple distributions, and we'll have a whole new discussion on how the elements come from different ensembles and what are different kinds of ensembles and what are different kinds of distribution. We'll have a whole discussion, but for now, let's accept this. The elements, they're random variables, they come from a distribution or an ensemble. So first, let's try to build the motivation of studying RMT, because if we know where we can use RMT, I believe we'll be more motivated to study them, and we'll try to use them in the specific places. Okay, why RMT is important? So let's say we have a very big data. Let's look at it from a data science perspective. If, say, we have a very big data and we want to see how my data are correlated, sometimes we don't only deal with matrices, but their eigenvalues. If you have a very big data, we might be interested in how the eigenvalues are, or what the spacing between the adjacent eigenvalues are. And that is what is important, because they will let us see how things are correlated. So first off, it's, if we have a big data, we will try to see how things are correlated. For that, we need RMT analysis, are correlated. So this is where I should stop and tell you a bit of history of how RMT came, or how the idea of random matrices came. It was during the 1920s, I believe. A person named Wishart, he tried to see how different data could be correlated. He tried looking at their eigenvalues and whatnot, and he picked the matrices from a distribution. So from that, it was mostly from a statistics paper in the 1920s. He wrote it in a statistics paper. So from that, the idea of RMTs basically came. But he wanted to study how things are correlated, but RMT story becomes interesting in basically the 1950s. We'll learn about this more explicitly in the next video. It's by a person called Wigner. He's a physicist, and he applied the idea of random matrices, and he basically developed this field for probably the most among all of the person working in the field. So this is in let's say this is the application in data science, or let's say statistics. Let's see how we use it in physics. In physics, there are many applications, but I'll just mention two of them. First one is in quantum chromodynamics, QCD. It's a theory of quarks. It's a theory of quarks. The particles that make up protons and neutrons, they're the most fundamental particle if you're seeing from a field theory analysis and so on. So it's the particles that make up, it's a theory of the particles that make up, let's say, protons and neutrons. So when you're studying this theory, you replace something called the Feynman graphs. A lot of you have heard about it. Feynman graphs are replaced by something we will extensively study in this course, is ribbon graphs. So they are replaced by ribbon graphs of random matrices. So in QCD, you have a pretty much a lot of application of random matrices. Recently, the more interesting thing of why I studied random matrix theory is because of its application in two-dimensional gravity. So a lot of you might know that a quantum theory of gravity is an unsolved problem in theoretical physics. It's been unsolved for a long time now, and I believe a lot of us are into physics for this. So there's this idea of something called holography. So a lot of you might know this, and the idea is basically, before going into the idea, let's say first why it's unsolved, a quantum theory of gravity. Because we now have two theories: the quantum mechanics, the theory of, let's say, the fundamental particles, quantum mechanics, and general relativity, the theory of gravity. But we cannot unify both of them. So it's an unsolved problem because we physicists want to say, we physicists want a theory of everything, so that a theory that can explain every fundamental forces. But we don't have a theory of gravity included with all the other forces. And holography is basically an idea, or it's a conjecture in the quantum gravity field, that a theory of gravity, it says that the idea is a theory of gravity in, say, d dimensions. D is the number of dimensions, is equal to a quantum mechanics on the boundary in d minus 1 dimensions. So this is the idea of holography, and a recent breakthrough has come in the two-dimensional field, two-dimensional theory of gravity, and that is due to the simple and powerful tool of random matrices. So you understand how powerful and vast the field of random matrices is, because you have a whole range of applications. And a lot of you won't understand a lot of things about, but this is a motivation video, so you know what the applications of RMT are. A lot of the things I say will go over your head, and it's obvious, but if you know where we can apply random matrices, it might motivate you to study these things. And we won't necessarily study 2D gravity and all those things in this course. So there's that. So, and there are other fields of physics where it's interesting. One of them is quantum chaos. We have disordered systems. Let's see. It's random matrices are important, have some application in string theory, and in mathematics there's knot theory, there's integrable systems, and one of the applications that we will see is in number theory. we will see this. We will learn more about this. We'll try to see the application of random matrices in number theory. This is all physics and mathematics applications, and there is also application in telecommunications. If you are interested in that, we apply random matrices to telecommunications. And in biology, you have something that I mentioned before. We will extensively study these things, something called ribbon graphs. So RMT models, let's write it down. RMT models that generate ribbon graphs predict the shape of RNA. So if you are interested, if you learn random matrix theory pretty well, and if you're from a biology major, and you can surely apply random matrix models which generate the ribbon graphs to study RNA and various other fields if you're interested. Okay, so this sums up the fields where RMT is important. I might have missed a lot of fields, but RMT is in general very important for studying various problems in the physical world. Okay, so let's now move on. Okay, so what is the main game of RMT? The main game of RMT is always dealing with the eigenvalues. Let's say study of eigenvalues. So we want to know how let's say there are two eigenvalues, lambda 1 and lambda 2. We want to know what the spacing is. Let's say what is the difference, what is this number? Because if you just think about it for a second, in random matrix theory, your elements, that is, let's say a11, a12, a21, a22, if you're considering a 2 by 2 case, these are random variables. These are changing like with every realization. Every new matrix you pick will have different numbers with in these entries. So the eigenvalues will be different as well. So RMT, a problem of RMT is always there to find, let's say, how the eigenvalues are spaced. So for different values of the entries, how my eigenvalues shape, or how this S changes, or how if this S is part of another distribution as well. This is the main game of RMT. So if we are looking for a definition, a random matrix is so let's see an example. So let's choose Aij, the elements of the matrix, that is -1 and +1. That is, our entries can only be -1 and +1. And let's also consider this. And if you remember, this is the condition of a real symmetric matrix. So we are dealing with real symmetric matrices here. Okay, so now let's consider cases of matrices with different sizes. Now let's say n equals 1. So the matrix, let's say in this column we write the matrix we write the eigenvalues and let's say the probability of getting that eigenvalue. So in a one-dimensional case, it's basically a scalar. So you have two possible scenarios. Either your matrix is equal to 1 or it's -1. So, and the eigenvalues are same, +1 and -1, and the probability of each of them is half. Now what about n equals 2? Say you have, and the eigenvalues are 0 and 2, and the probability of them is 1/8 of getting eigenvalues 0 and 2, and there are 8 such matrices, and probability of each of them is 1/8. So this is the example of, let's say, this is the example where my entries can only be -1 and +1. So let's say for general n, in this case, for general n, we have, okay, let me write this like this, matrices. So if you can check this for yourself, just plug in 2, and 2 times 3 is 6, and you have 8 such matrices. Right? 2 cubed is 8. Okay. So the probability of each of them is two. So let's say for n equals 2, the probability of each of them is 1/8. So we can always deal with this kind of matrices, and we'll have special matrices in this example as well. Special matrices in the sense that, like, there will always be elements with everything 1, like this. For example, in 3 you'll also have something like this in every example. In every size of the matrix, you'll have a matrix where all the elements are 1. You will also have matrices where all the elements are -1. So, and the eigenvalues of those are, let's say, in this case, lambda equals 3 and 0. For the negative case, where all the elements are negative, that is -3 and 0. You can check this out for yourself. Now, why are we doing this? Because we want to study the behavior of eigenvalues. We want to see how eigenvalues behave, even in this specific example. So, important question. How do these what does that mean? First, you see, for different n, we have different eigenvalues, and we want to see if these eigenvalues have a structure. So how do these eigenvalues behave? If you pick a 100 cross 100 matrix, you can see that the eigenvalues are like this, with, of course, a normalization. Your eigenvalues are distributed like this, and if you note, it's rho of lambda here, which is the density of eigenvalues, and here it's just lambda. And for, let's say, a 3000 cross 3000 matrix, it looks something like this. So you see there's a pattern forming, right? It's sort of like a semicircle, and it becomes more clear when you take a bigger one. If you have a computational power, check for, let's say, 4000 cross 4000, or let's say you start with 5 cross 5 and go up to, let's say, 500 cross 500. If you have the computational power, just check them and see if you if you sort of understand the structure by, yeah, see, by getting a semicircle or something, because this here is sort of like a semicircle, right? So Wigner's idea was, if you take n goes to infinity, you end up with a semicircle. This is pretty apparent from here, because if you see, we are already getting a structure from like an n goes to infinity. So here, this is an n goes to infinity scenario. You have a full semicircle. So in case of, let's say, a real symmetric matrix like the one we considered, you can even try without normalizing as well. Real symmetric n cross n matrix, the eigenvalues will be between plus minus, and you will see a semicircle forming. The bigger matrix you take, the more you will realize that it's just a semicircle. This is the famous Wigner Semi-Circle law, which we will come back multiple times in the course. This is the famous Wigner Semi-Circle. I just wanted to build a motivation for the Wigner Semi-Circle law. It is, if you take more matrices, bigger matrices, you will start to see a semicircle like structure, and that will be more apparent, rather than, let's say, 100 cross 100 matrices won't give you much of a semicircle like structure. But if you take a bigger matrix, you'll of course have a semicircle like structure. Now you might say, well, we picked AI. Is it because we picked Aij from -1 plus 1? Is it the case? Is it because of just this? No. If you pick your Aij from any one of your distributions, any distribution you like, or let's say you pick Aij from random numbers like this, you still get the Wigner semicircle. You still fall under Wigner semicircle law. Also, you can try taking Aij from an ensemble, that a distribution that you learned recently, the Gaussian distribution. And guess what? All give you all of these, let's say, all of these gives you the Wigner semicircle. Circle distribution. So this is the idea I wanted to build up at the introductory lecture of this random matrix course, and I believe there are a lot of things that went over your head. Of course, it's pretty understandable, especially the part when I tried explaining how random matrices are important in this context. But yeah, in this case, I believe it's pretty it should be pretty clear, and it should make you think why there is such a semicircle distribution we have. Thank you.